Good morning, students. Today we will start with the transfer function. Previously we have read about the Laplace transform and its inverse. In that case we presented the idea of the partial fraction expansion and how to find the inverse Laplace transform also. As we already know that in the previous lectures that we have discussed that this transfer function allows us the separation of the input system and output into three separate and distinct parts. That is, we will get the three distinct parts in this case, like this output system and the input. So we get the three distinct parts, and also we can algebraically combine these different parts by using some mathematical operations in that. So it is very easy to solve when we are using this approach. And now let us suppose that first of all let us consider a differential equation. First of consider the nth order differential equation. In this nth order differential equation, Ct is the output and Rt is the input. That is, Ct is the output and Rt is the input in this case, and Ai and Bi, these are actually the constants. So it is actually a linear time invariant equation, LTI, linear time invariant equation. So now we will discuss about that what is the linear time invariant equation, and the Laplace transform can only be used for these linear time invariant equation. So a linear equation actually can be recognized by its form, that is, it is linear if the coefficients of y, that is the dependent variable in this case, and all other derivatives of the y are the functions of t and constant terms, that is coefficients of y and all other derivatives of the y are the functions of t and the constant term only. Now there are few examples of that, like let us suppose here we have dy by dt equal to 4t. It is a linear differential equation. D square y by dt square equal to 6t. It's a linear differential equation, and t dy by dt equal to 6. It is a linear differential equation. Now the example of the non-linear is written here. It is dy by dt ka whole square, so it is a, and t square is there, so it is a non-linear differential equation. Now the second requirement is the time invariance. First is the linearity and second is the time invariance. Now if we use the same input at the starting condition for a system, and sometime later we will get the result, and at some time later that is after some time shifting we will give the input, so output is also shifted by time, that is it is invariant of the time. So then we can say that it is time invariant. And now let us suppose that we gave the input, in the first case we gave the input as ft and we will get the output as yt, and time shifted. If the system is time invariant, then if the function is t minus, let us suppose 6t, then the result would be yt minus 60. So it is a linear time invariant equation. Now this equation that we have considered is a linear time invariant equation. We take the Laplace transform in of this equation and we get this. Finally we also neglect the neglecting the initial conditions, we will get this equation. Now equation can be represented in terms of output divided by the input. In this case you will see that C is the output and Rs is the input. Now the equation can be represented like this, that is Cs by Rs, which is actually the transfer function representation of the equation. So this GS is known as, it is represented by GS, that transfer function, and RS is the input in this case, and CS is the output, and this is the block that is represented. So in that case, we represented this differential equation into three separate entities. Now this is only possible if the equation is LTI, linear time invariant, that we have discussed. So we can find the transfer function only for the linear time invariant systems. Now let us consider a small example that how to find this transfer function. Now let us consider the system. So we take the Laplace transform on both the sides. So far we have one derivative here, and initial conditions are 0 in this case. So 2CS equal to RS, and after that the transfer function is given by output, by input, that is CS by RS equal to 1 by S plus 2. Now this is the transfer function of the system. Now let us suppose that we want the response of the system for the unit step input. We know that the transfer function of the unit step input is 1 by S. So we want to know about the response of the system. So what is the response of the system for the unit step input? We take this equation, that is GS into RS is equal to CS. CS is the output in this case. So RS in this case is input, which is this unit step, and GS we already know that 1 by S plus 2. So 1 divided by S into S plus 2. So we expand it by using the partial fraction expansion that we have discussed previously, and after the partial fraction expansion we get this value, and we take the inverse Laplace from that. We already know that the different values are available for that is 1 divided by S plus 2 and the 1 by S. What is the inverse of that? From the table that we have discussed, that is 2.1. So from that we can find the what is the value of the C, what is the output for a unit step input. If the input is unit step, so what would be the output? So from this transfer function approach, it is very easily we are able to get the result, that what is the response for the unit step. If the response is if we want the response for the impulse, we can get that. If we want the response for the ramp, we can easily get that also in this transfer function by multiplying the transfer function only. Now we want to know about the transfer function for the physical systems. We already know about how to drive the transfer function for an ordinary differential equations, that is how to write it and then how to find the transfer function out of that. So since we want to model the physical system in terms of transfer function, so now we will discuss that how the physical systems we can model the how can we can find out the transfer function for the physical systems. Now let us consider we have this electrical system. We first consider the electrical system. In the electrical system we have the capacitor, resistor and the inductor, that is standard elements. Then we have the voltage current relationship that you have already read in the basic electrical. Voltage, the voltage capacitor relationship. Then in second case we have this that is voltage and current relationship in this case, and the voltage current relationship in case of inductor. Then we have the current voltage relationship, that is I equal to C dV by dt. So it is the current voltage relationship. Then we have current voltage relationship in case of resistor, and then we have the current voltage relationship in case of inductor. Then we have the charge, as we know that this current is equals to dq by dt. So it is voltage charge relationship that is there. So now in impedance, now we have calculated the impedance here, and then we have calculated the admittance there. Now how we have calculated the impedance in S domain. Now let us consider this this IT equal to C dV by dt. So in S domain we can write it as IS, that is Laplace transform, that is it is differentiation. We can use the Laplace transform in that, and this is CS that is we will we have IS is equal to CS SCS and VS. How to calculate the impedance? That is, which implies that VS by IS, sorry, we have to use I large in S domain, which is equals to 1 divided by CS. So that is 1 divided by CS. So we get 1 divided by CS. Similarly for the resistance and for the inductor, since we have integration part, so we get impedance as LS. Admittance is opposite to impedance, so we can get CS and then G, that is the conductance in this case, and 1 by LS. So we will have this in S domain also. We will have this impedance and admittance, which in the subsequent lectures I can show you that how what's the importance of this. Now we can discuss the transfer function for this electrical network. Let us consider that we have the voltage source applied to DC voltage source applied to the inductor, resistor and the capacitor. So how the Laplace can be used in this case, we have to discuss this. Now first of all, we must know about that what is the input and output in this case. That in this case that we know that output is voltage that is required is VC, and input voltage that is required is this VT. Now let us consider electrical network. So first of all, to solve that network, we want to know about the output and the input in this case. Designer must know that. So in this case the output is VC and input is VT, so we have to find the transfer function. So assuming the zero initial condition. Now let us suppose that now we use first of all we use the KVL in this case, that is as you already have read in your previous year about this KVL and KCL. So KVL equation is this: changing variables from current to the charge. The current can be represented like that. Now from the previous table of the voltage charge relationship for a capacitor is given by this. Finally we are getting this equation. Now we find the Laplace of this equation, previous equation, assuming the this zero initial conditions. That is, initial conditions would be zero in this case. So we find the Laplace of that, and finally we are getting this equation. And finally output in this case is VC and input is VS, and we are getting the final equation as 1 divided by LC divided by S square plus R divided by LS plus 1 by LC. And finally we get this block diagram representation. Input is VS, output is VC, and this is the transfer function that we have discussed. So this is the case. We have to write the differential equations and then simplify it and apply the Laplace in that. Instead we can also use another very simplifying technique for the solution. As we already know from this previous table that we have discussed here, that is impedance and admittance. So we use this table. As we already know that for a component, resistive component, the Laplace transform is this: Vs equal to RIS. For an inductor it is Vs equals to Ls into Is from that table, and also for an capacitor Vs equal to 1 by Cs into Is. So also we have the impedance Zs. Now we will use a very simple method. We will simplify this thing, that how to find in simplifying terms that transfer function. Now what we do, again diagram we will take this one, and again we write everything in S domain, that is Vs, then we have Vc, then in this case we get Ls, that is impedance in this case is Ls, that is discussed in the table, then R, and this is 1 by Cs. Okay, so instead of writing that in time domain and then convert it into this S domain, we are writing simply in this terms and consider it as an impedance. And finally we will write it as use the KVL with while having these values. We use the KVL, that is Ls into I, it gives the value of the voltage here, then R into I, voltage here, then 1 by Cs into I, voltage here, that is capacitor, which is equal to Vs. And finally we will get the output and this Is and Vs relation as 1 divided by Ls plus R plus Cs. Now the voltage across the capacitor can be obtained by simply using this relationship, that is the voltage across the capacitor is equals to Is into, that is Is into 1 by Cs, which is the impedance of capacitor in this case. So in this case, without writing the differential equation, we have simply used this KVL and find out the value of the transfer function. Now let us consider, we can do also this example we have done with this mesh analysis. Then let us suppose that if we want to do the same and by using the nodal analysis and without writing that equation, we can simply do that. That is we can write the node equations, and after writing the node equations, simply we can find out the values without writing the differential equation, and we will get the transfer function, that is VCS divided by Vs, also by this nodal analysis. So in these examples you will see that by using this transfer function approach, the problems, the physical problems of the electrical are very much simplified, and we need not to work on the differential and the integrals, and as a result we can get the result very easily as compared to these differential equations. So it's the best way to do, and it is one of the important part of that that is electrical engineering also. That is the transfer function approach by using the Laplace. So I will give the problems related to that to you in your assignments, and you can I hope that you can understand well that how to do the analysis, and you can do. Now in this we have discussed about the electrical system transfer function. The next we will go for the mechanical system transfer function, so that we can have some view of that how this mechanical system can be converted into these transfer function. That is how we can find the transfer function of mechanical system. So then after that you have to learn about how to do cascading of that, how the simplification can be done. So it finds importance in the electromechanical system. Let us suppose that we have one system which is electromechanical. I will show you the example of that electromechanical system. Now this is the electromechanical system. It is a NASA flight simulator robot arm with the electromechanical control system. So you will have the electrical systems in that which works and gives signals, and the mechanical systems move. So the importance of the transfer function is that you can represent every system in this transfer function and every part of this electromechanical system. So it is one of the important part of any industry, that you have the electrical systems and you represent those electrical system in terms of transfer function. Then we have the mechanical systems, you represent those mechanical systems also in transfer function. So this is the finest example of the electromechanical system, and that is where the usefulness of this lies. I hope you understand well that why we are doing this. We can discuss also with time that how we work on the different aspects of electromechanical system, and hope we can also do some example of that type, and we can do some simulation also. So this is the finest example of this electromechanical systems that we are using. It's a practical example. This is all about that. Now we will, in the next lecture we will start about this mechanical systems. Thank you.